Good morning. So I'm starting the part which was already started yesterday. So I was explaining the method 3 of finding the steady state error. This is the last topic in this steady state error calculation. So yesterday I had shown you that whenever you are finding steady state error, it is nothing but input minus output, and this is the error. It has to be calculated at t tends to infinity. Now, whenever you are calculating the steady state error from output response, so this is a special name of this topic. In that case, only one thing we have to assume that HS has to be kept as 1. So in this case, I have taken this experiment. I was explaining this thing to you yesterday. So I have taken one GSHS, that is actually 2 by S plus 5. So this is the 2 by S plus 5. And for this kind of calculation, always we have to assume it's a unit feedback system. So for this method, always assume that GSH is equal to GS, or assume HS, that is the feedback, is equal to 1. First step, find TS equal to GS by 1 plus GSHS. We are finding that this is 2 by S plus 7. Step response, CS is equal to RS into 2 by 7. Substitute RS as 1 by S, 2 by 7, 7 plus 1. Then we are finding Ct is equal to 2 by S, 1 minus e raised to minus 2t by 7. So this thing is having two parts. One is the static part, 2 by 7. Another is the time dependent part, and this part is diminishing. So if you are going at t tends to infinity, Ct will become 2 by 7, because this 2 by 7 into e raised to minus 2t by 7 part will become 0. So final ESST is equal to 1 minus output at t tends to infinity. Ct you can find at t tends to infinity. This is 2 by 7. So input is unit step, input is 1, and output as t tends to infinity is 2 by 7. So final steady state error is 5 by 7. So this much part we could calculate, or we could understand yesterday, and now we are supposed to see is how to visualize this. So this is the first thing we have to do. So this is what we have found out, steady state error from output method. So in the first method we were finding the equation of ET, and then we are substituting ET tends to infinity. We are finding what is the steady state error. Second method, we are not calculating anything about ET. Directly from Kp, Kv, Ka, we were calculating how is ET at t tends to infinity. This is the third method. This third method, we are finding Ct. Ct is the output. So 1 minus output is the error. So this is in case of unit step input. So finding ESST for GSHS 2 by 5 by method 1. So whatever we have found now, just now, you have to remember this error, that is output is 2 by 7. So in this case, output is 2 by 7 at steady state, and 1 minus 2 by 7 is equal to 5 by 7. So this error is equal to 5 by 7. This you have to remember. Now what we will do is we will go for finding or validating the same thing by using second method. Sorry, first. What is the first method? So all the methods I am showing together. What is the first method? ES is RS by 1 plus GSHS. So you are finding S plus 5 by S plus 7 into 1 by S. From there you have to do final value theorem. So all the methods. So I am telling to all my students. So I have written around 13 pages. 6 pages are already uploaded. The 7 pages I am going to upload it today after this lecture completion. So this 13 pages, every nook and corner you have to understand. Fundamentals are very simple. Fundamentals are repetitive, but there are many fundamentals that you have to write. So ESST, that is t is ET at t is equal to infinity, that is limit s tends to 0. So either you can find from t domain or you can find from s domain. If you are finding from s domain, the formula is limit s tends to 0 SES. Or if you are finding from t domain, it is ET t tends to infinity. So ES we have already found out. So ES is RS by 1 plus GSHS. If you substitute this, you are finding ESST is equal to 5 by 7. So this processes you have to go. So this is the first method, that is method 1 that we have already found initially. So from method 1 also we are finding it is 5 by 7. From method 3 also we are finding by 5 by 7. So method 3 we are finding the output, and we are subtracting output from the input. So input is unit step, that means amplitude 1. So 1 minus 2 by 7 is 5 by 7. That was the first case. In this case, method 1 we are finding from limit s tends to 0 SES. So this is from final value theorem. So same error can be found out by 3 methods. First one is from final value theorem, that is limit s tends to 0 SES. Next, from second method. Second method is finding from static error constant. So whenever I am inputting unit step, in that case you have to find static error constant as Kp, because for unit step input we find out steady state error by Kp. So what is the error formula in that case? 1 divided by 1 plus Kp. So now Kp you have to find out first. So in the second method, first I am finding what is Kp. So Kp is equal to limit s tends to 0 GSHS. GHS is already given, so limit s tends to 0, 2 by s plus 5, that is equal to 2 by 5. And now you have to plug in this 2 by 5 in this formula. So I told you that if it is unit step, it is 1 by 1 plus Kp. If it is 3 of unit step, in that case, this will be 3 divided by 1 plus Kp. 10 of unit step, that means you are giving 10 volt input. In that case, this will be 10 divided by 1 plus Kp. So the same error will be multiplied by 10 times or 3 times or 5 times if the input is a unit step or 5 unit step or 10 unit step, depending on that. So there is nothing confusing about that. So in this case, we are finding Kp finding is very important. So Kp limit s tends to 0 GSHS. So GSHS 2 by s plus 5. This initially. In this case, what we are finding is limit s tends to 0, GSH is equal to 2 by 5. So that is the Kp value. Substitute here 1 by 1 plus 2 by 5, we are finding 5 by 7. So this is the method number 2, that is finding the steady state error from static error constant. This we are finding 5 by 7. Previously, I had shown you the method number 1. In this case, we had been finding the error from ES, that is the final value theorem, that is limit s tends to 0, s into es is equal to rs by 1 plus gshs. And in the third case, this is actually method 3, we are finding the steady state error from calculating the cs, and from cs we are finding ct we are finding at t tends to infinity. This is ct at t tends to infinity. Whatever we find ct at t tends to infinity, this if we are subtracting from input at t tends to infinity, so this subtraction is giving me what is the error. So this 2 pages, if you just do it, you will understand all the 3 methods. So this is method 3 is given first, then method 1, then method 2. So this is what we are doing is, this is a type 0 system and we are giving step input. How the output looks like. So whenever we are talking about method 3, in that case, this is the input and this is how the output looks like. So this is 2 by 7 into 1 minus e raised to minus 2 by 7. So if you are substituting t is equal to 0 in this case, you'll be finding that the output gets stabilized at 2 by 7. So this is the final value of ct. And input is actually unit step. Unit step input means input is actually 1. So in this case, how much is the steady state error? This is 1 minus 2 by 7, that is equal to 5 by 7. So either you go by method 1, 2 or 3, or you go by image or response analysis. Every time you will be finding to the same error value, that is equal to 5 by 7. So let us see what is written. So 5 by 7 is equal to 1 in previous page ESST by method 3 is equal to 2 above ESS method by method 1. So this is the final value theorem method. This is method 2. This is the static error constant method. So we are having 3 methods: final value theorem method, static error constant method, and finding the output, finding the error from the CT method, that is from the response. So this is the response method, whatever I am showing. So one very important thing is we are given GSHS or HS equal to 1. We are actually given GS. Okay, so GS is an open loop transfer function. So the very big significance, it is written in the books, but student overlook it. You can write down in your own language. That is, we are calculating actually how much will be the steady state error of a negative feedback closed loop system. I will repeat, we are finding how much is the error in the negative feedback closed loop system, and what is given? Given is only open loop transfer function. So this is a very important concept. I told you that GSHS does not have any physical significance in control system, but from calculation point of view or from analysis point of view, this open loop transfer function is having tremendous implication. What is the open loop transfer function? GS or GSHS? GSHS is given here, and from the open loop transfer function GSHS, we can find out what is going to be the steady state error of the closed loop system with negative feedback. So if somebody asks you what is the significance of calculating all the steady state error, this answer you have to give. For the third time I'm repeating, that is from the given OLTF. So this one line question will be asked from the given OLTF, that is open loop transfer function GSHS, we can calculate what is going to be the steady state error of negative feedback closed loop system. So from the stability of open loop transfer function, we can estimate what is going to be the stability of closed loop transfer function. Because if this output is getting steady at a certain value, that means this is a bounded kind of output. Okay, in that case, the system is not going to be unbounded, or system response is not going to be unbounded. So system will be kind of stable, marginally stable here, but at least it is not going to be unstable. So how are you calculating it? You are calculating everything by GSHS. So from open loop transfer function, we can calculate what is the error of the negative feedback closed loop system, and from there we can find out what is the stability. And I have given you three methods. Okay, first method is by final value theorem, second method is from static error constant. So that is the easiest method, उसमें कुछ समझने की जरूरत नहीं है, just calculate kp kv ka 1 by 1 plus kp 1 by kv 1 by ka, you are finding how much is the error. कुछ समझे ना समझे चलता है. But first method and third method you have to understand, because first method you are actually finding or applying the final value theorem, and third method requires too much of understanding, because third method first you are finding what is the system output CT, then you are finding what is the system output CT at t is equal to infinity, so that is 2 by 7, and then you are subtracting that final value from the input final value. So input is actually steady at 1, output final value is 2 by 7, so 1 minus 2 by 7 is equal to 5 by 7. This is called a steady state error. And yesterday also during lab, that is on Tuesday, Kiran asked, sir, why can't we find out error here? You cannot find steady state error here, because here the waveform is still increasing. Let the waveform come to steady state first. Okay, and then you find out what is the difference between input and output. That will be the steady state error. So in this method, in this third method shown in the previous page or here also through this diagram, step and step response of the system is found. This is a type 0 system, that is 2y plus 5. So when the response is subtracted from the input steady state, we get a steady state error. So error at output at steady state, which is subtracted from input at steady state. So 1 minus 2 by 7. You are finding error at time is equal to 0. In this case, error will be 1. Okay, because in this case, input is 1 and output is 0, because output has started building. So you cannot find steady state error at t is equal to 0. You have to find steady state error at t is equal to infinity, because here the waveform has taken some kind of a stable value. So when this response is subtracted from this, so this response is subtracted from the input at steady state, we get steady state error. So ESST is equal to input minus output at t tends to infinity. That is, input also has to go to the infinity, output also has to go to the infinity, and then we can find what is the steady state error. So all these notes are given to you. Now the same type 0 system, and to tell you second type 2 system, I could not show you that day. Okay, that's also very interesting set of output, but I have got the code. So the code is written in a very proper fashion now. So all the codes will be uploaded, and you can find out steady state error for all three systems, that is type 0, type 1, type 2, for all three inputs, step, ramp and parabolic. And there is a table of 3 by 3 that you have to satisfy through your experiment. So experiment 6 is now clearly defined, and all the codes we are having, I'll be giving you all the codes. This is very simple. You'll be able to generate all the 9 waveforms, that is type 0, type 1, type 2 system with step input, ramp input and parabolic input. So all the codes are there, you will get it. Okay, so find the ESST for the unit ramp input. Now, this case you have to understand. So this is a type 0 system, 2 by S plus 1. Input is unit ramp. So by method 2, if you are going, in that case, what you will do is first find what is KV. So KV is into GSHS. So you'll be finding KV is equal to 0. And what is the error unit ramp input? It is 1 by KV. So these are the three formulas you have to remember. If it is step input, any system, type 0, type 1, type 2, error will be A divided by 1 plus Kp. A is the amplitude of the step. So if it is 2 step, in that case, A will be 1. For unit step, A will be 1. Okay, so for 2 unit step, A will be 2. For unit step, it will be A will be 1. So in this case, unit ramp, so A is equal to 1. In this case, how much will be the steady state error? So first we have to find out by method 2 what is KV. This formula is given as GSHS. Substitute GSHS whatever we have already assumed. So this is a type 0 system. You are finding KV is 0. In that case, steady state error is 1 by KV. 1 by 0 is equal to infinity. Okay, so response CT will be an increasing function with time, hence the error ET also will be a diverging function. So in this case, what we'll be finding is input and output both are increasing like this, and both will be increasing in a different gradient. So as time goes by, they will be diverging. This graph we will show you, or already we have seen this graph during our lab, that is type 0 system with step, and both are diverging. In that case, the steady state error will be infinity. Same thing happens for parabolic input also. So this is CS is nothing but this is the output. So ESST for unit ramp using method 3. So previously it was by method 2, that is we found by KV. Now we are finding what? The same thing, that is the ESST for unit ramp input. I'm sorry, I told you parabolic input. This is for the ramp input. We are finding for the same system how is going to be the steady state error. So this is type 0 system, and type 0 system actually is equal to 2 by s plus 5, whichever is shown at the above. You can find here 2 by s plus 5, but first we have to do is we have to convert this thing into a CS by RS, that is GS by 1 plus GSHS. So if you do that, 2 by s plus 5 divided by 1 plus 2 by s plus 5, you'll be getting it 2 by s plus 7. Okay, so this is method 1, where first we find what is CS by RS. So this is 2 by s plus 7, was found in page number 7 previously. Now what is CS? CS is equal to 2 divided by s plus 7 into RS. Now what you have to do is you are inputting actually ramp input. So in case of RS, I have to substitute 1 by s square. So CS, so the same system, that is 2 by s plus 5 is the GSHS. Closed loop system is 2 by s plus 7. For this system, I have to find what is the output response if I am giving ramp as the input. So ramp means 1 by s square. So now I am in the third method. So third method is all about find out CT. So while finding CT, I have to use CT is equal to, or CS is equal to RS into transfer function. So take this RS here, substitute RS 1 by s square. So this is 2 by s square s plus 7. Now if you are finding CT by inverse Laplace of this partial fraction, you have to do. So in that case, what you are getting is CT is equal to 2 by 7, 2 by 49 e raised to minus 70 minus 2 by 49. In our lab, I told you that there are 3 parts here. This is the static part. For any kind of time, this minus 2 by 49 will be there. So this DC is not a time dependent part. This will always be there, minus 2 by 49. Now this 2 by 49 e raised to minus 70, this is a diminishing part. As time increases, this part will become 0. And 2t by 7, this part will be diverging. So this is the unstable part in the output. This thing will make the output unstable because there is a ever increasing part. Input is T. Okay, T means at any time amplitude is same. At T is equal to 1, output is 1. At T is equal to 100, output is 100. That is slope is equal to 1. So that and this CT, you have to find the difference between T and 2 by 70, 2 by 49 e raised to minus 70 and minus 2 by 49. So that is the error function. So what is the error function? Error function is T, that is the input, minus this CT. That is the error function. At this T minus CT, you have to take at T tends to infinity. So if you do that, so input is T and this is the output. So input minus output at T tends to infinity. So T minus 2t by 7 plus 2 by 49 e raised to minus 70 minus 2 by 49. If you do that, you are finding that there are 3 parts that already I have explained, that 2t by 7 goes to infinity at infinity. 70 converts the T to infinity, and 2 by 49 is a constant, is a negative term. So at T is equal to 5 seconds, CT is equal to 2 is equal to 1.39. So finding that at T is equal to 5 seconds, T is equal to 1.39. And second input is equal to 5. So this whatever CT you are finding at T is equal to 5, you'll be finding that that is equal to 1.39. And T is equal to 5 if you are giving to the input. Input is 5, so input is 5 at T is equal to 5 seconds. Output is 1.39. Difference between that is nothing but 5 minus 1.39, that is 3.61. And at 5 seconds we have found like this. At 10 seconds you will be finding that this is increasing. 15 seconds you will be finding that this is increasing. So this is a graph which is shown in the next page. This students are not understanding this. Sir, how can you say that a steady state error is infinite in case of this is a zeroth order system and this is a ramp input? Okay, so this is a graph between input and output. This was shown. So whatever this line I have shown, this line is nothing but the response of CT, whatever I have shown in the previous page. So what is the response of CT? CT was 2 by 70 plus 2 by 49 e raised to minus 70 minus 2 by 49. So this graph CT, 2t by 7 plus 2 by 49 e raised to 70 minus 2 by 49. This graph is actually shown by this below line. Okay, so this below line is nothing but that output graph. And input is increasing very fast. And if you are finding that distance between input and output is increasing with respect to time. Okay, so above is the input, that is TUT. Below is the output, that is the CT for 2 by 7 plus 5 GSHS system. And the distance between them is increasing with respect to time. And as we find steady state error at T is equal to infinity, what we will be finding that this distance between input and output at T tends to infinity, it will become infinity. So it is actually a two diverging graphs. So whenever T tends to infinity, this distance is also going to increase. So that's why it is called as type 0 system for ramp input. this is going to have a steady state error of infinity. So whichever you have proved in the previous page, you have proved it here. Okay, by the method number 2, you have proved it here. That is, kv was coming to be 0 and ESST is coming to be 1 by kv. That is 1 by 0 is equal to infinity. So this infinity you are proving by the third method. So in the third method, you have found what is the CT, and the CT you are plotting, that is the output you are plotting and input you are plotting, and you are finding that this distance is ever increasing. Okay, and that's why we are saying that at t tends to infinity, distance between the input and output will be is equal to infinity. So this finishes the second response, that is the type 0 system, and this is with a ramp input. Okay, type 0 system with a ramp input, and we are finding the steady state error is infinite. So next, error for type 1 system will be, so next what you can do is you can do the same thing, that is you can take a parabolic input, and for parabolic input also you will be finding like this. For the parabolic input also you will be finding here, if you are substituting instead of SGSHS, you will be substituting S square GSHS. Okay, S square GSHS will be finding that is also going to be 0. In that case, what is the KA? KA actually is going, and what is the data for parabolic input? That will be 1 by KA. Again, that will be infinite. So whatever response we have got here, same kind of response you are going to get, but instead of a linear line, it will be a parabolic kind of line. So input also will be parabolic, output also will be parabolic, and you will be finding the distance between input and output parabolic is actually expanding as the time is going on. So that is the third case, the input type system. Things we can prove, it's not a big deal. Whenever you do the coding and all, you will find it. Now we are entering, so one thing we're skipping here, we have skipped actually, there is a parabolic input and type 0 system, we have skipped that. Let us directly go to the type 1 system. Okay, so type 1 system is the very important thing, because there are 3 cases which we find here. To input minus output, and this input minus output, whatever function we get, that we will take to t tends to infinity. So this is the third method explained in brief. So that is find output CT. So what will be given is, given will be GSHS, or actually given is GS, because HS is equal to 1. So first find what is CT. CT means we find first what is CS by RS, or we find first what is TS. Okay, there we find CS is equal to RS into TS, and there we substitute RS is equal to 1 by S or 1 by S cube, depending on whatever is the requirement. So first what we are doing is, for the same system, not for the same system actually, I have changed the system. It is 4 by S into S plus 5, we have made it for a certain reason that I will tell you why. Okay, so unit step, so this is type 1 system, GS into HS is 4 by S into S plus 5. So first you have to understand that this is a type 1 system. Why this is a type 1 system? Because there is a S term here at the denominator of GSHS. H is equal to 1. There is a pole at origin. Okay, whenever we are finding GSHS, so HS is equal to 1 assumed. So for GSHS, there is a pole at origin. That's why this is a type 1 system. So first find what is TS. TS is nothing but CS by RS. That is GS by 1 plus GSHS. If you are calculating it, it is coming to be 4 divided by S square plus 5S plus 4. Now, a request to you, whenever you are doing the lab experiment and whenever you will be generating coding, you take this GSHS in such a way that, so you have to be a little tricky. You have to take this GSHS in such a way that this denominator is factorizable. Okay, so take this GSHS in such a way that this denominator is factorizable. So in this case, I have taken this 4 divided by S into S plus 5. So you have to take this A divided by S into S plus B in such a way that A square plus BS plus A, this will be factorizable. So in that case, your response will become very easy, calculation will become very easy. This I did not keep in mind whenever I was doing the lab. Okay, but now I have found the trick, at least for type 1 system. So what you have to do is, this is A divided by S into S plus B. You have to take this A and B value in such a way that A square plus BS plus A is factorizable. So there are many factors. You can take all the poles in the left hand side of S plane. So this is also another trick, okay, how to define the GSHS so that we are going to make the calculation easy. This is just for ease of calculation. So type 1 system, 4 by S into S plus 5. If you are finding CS by RS first, it is 4 divided by S square plus 5S plus 4. Then find what is the step response. So step response means CS is equal to RS into 4 by S square plus 5S plus 4. So this is 1 by S into this. If you do the partial fraction, you'll be finding CT is equal to 1 plus 1 by 3 e raised to minus 40 minus 4 by 3 e raised to minus t. So here, this is the type 1 system and we are inputting unit step. And we are finding that CT is having three parts. One is a constant part, that is 1. Another two are diminishing part with respect to time. That means if we are finding that if we are substituting t is equal to infinity here, this part will become 0, this part will become 0. So what will be the output at t tends to infinity? It will be 1. What is the input given to the system? Unit step. It is already written here. Unit step is given here. Unit step. That's what we have taken RS as 1 by S, and we are finding that output CT at t tends to infinity is going to be 1. It means that at t tends to infinity, input minus output is going to be 0. It means that whatever output you are going to get, that is going to touch the input at t tends to infinity. So you don't need to do this test up to t is equal to infinity, because I have plotted this MATLAB, so I will upload it whenever I am uploading this note. You'll be finding that almost at 5.5 seconds you are getting output almost at 0.995 or something like that. So you won't have to go to infinity. Almost at 6 seconds or 7 seconds you will be finding that output is reaching to the input. So whatever graph we have found out, whatever CT we have found out, that is whatever output we have found out, 1 plus 1 by 3 raised to minus 40, this will be increasing, because this output is trying to catch the input. And what is the input? Input is the unit step. So 1 minus 4 by 3 raised to minus t plus 1 by 3 raised to minus 40, this will be increasing, and almost at 6 seconds you'll be finding input is touching the output, or output is touching the input. Same thing can be proved by using method 2. That is what? Same thing, that is steady state error is equal to 0. That you can prove by method 2 as well. What is the method 2? Find Kp, because input given as unit step, so find Kp. Kp is limit s tends to 0 GSHS, so this is 4 divided by s into s plus 5. Substitute 0 here, so this becomes 4 by 0 into 5, so this will become infinity. And what is the error? ESST. ESST is equal to 1 by 1 plus Kp, and Kp we have found as infinity, so ESST is equal to 1 by 1 plus infinity is equal to 0. Whenever I am saying that steady state error is equal to 0, that means output will touch the input. Okay, so this is the first case. In case of type 1 system, with unit step input, we are finding that the response is touching the output after a certain time. That means the steady state error will be equal to 0. And now we are coming to the most interesting thing and most okay, so there is a conclusion from here. So it can be verified from MATLAB that at 5.5 seconds the output, that is CT, is almost 0.994, almost equal to 1. So no need to go up to infinity at early stage only. That means at t is equal to 6 seconds, 7 seconds, you'll be finding that the output is actually touching the input, provided the system is with negative feedback. So given by OLTF 4 by s into s plus 5, whatever this OLTF system is generating, the closed loop system with feedback, that closed loop system response will reach to amplitude 1 at almost t is equal to 6 seconds. So conclusion, type 1 system with unit step input is having steady state error as equal to 0. So very important thing. Now you are coming to the most interesting response. I had shown it to you. Again, I am going to show it to you by a different, easier kind of an example. So the same thing I have taken. So this is the type 1 system, and I'm giving unit ramp input. What is unit ramp? So more than control system, we are actually doing signals and systems. Okay. So what is the unit ramp input? It is t into ut. Okay. So t into ut means it is a unit ramp. And what is the Laplace of that? It is 1 by s square. So t into ut Laplace transform is 1 by s square. GSHS is equal to 4 by s into s plus 5. So what is CS? CS is equal to 1 by s square into 4 by s plus 4 s plus 5. What is 4 by s plus 4 s plus 5? This is nothing but the TS. So we have found in the previous page also. So I have gone a little, I have done some little step jump. You can find here also in the previous case. This is 4 by s plus 1 s plus 4. So this is equal to CS. Okay, so CS is equal to RS into GS divided by 1 plus GSHS. So you should not get confused. In case of ramp, instead of 1 by S, we are putting 1 by S square. So that is the same thing we have done. That is, just give me some time. So this is the case. Next page. Sorry, I have come forward. So what is 4 by s plus 1 s plus 4? 4 by s plus 1 s plus 4 is nothing but the transfer function. So whatever transfer function we have found for the given system, GSHS. So this one is GSHS 4 by s into s plus 5. So there, if we are finding that closed loop system, this becomes 4 by s plus 1 into s plus 4. So CS by RS is equal to 4 by s plus 1 into s plus 4. Then take the RS in the right side and substitute RS as 1 by s square, and then take what is the inverse Laplace transform of this CS. So we are finding it is CT. Now this response also I had shown you. There are three parts. One is the constant part with respect to time, it does not diminish. There is another two parts which are actually diminishing with respect to time, and there is the first part which is actually ever increasing. And because of this part, this response is actually an unbounded response. Why this is called as an unbounded response? Because as t is increasing, t is going up to infinity, time is going up to infinity, ct also will go up to infinity. So this is the output, this is the output of the system. What is the input of the system? Input of the system is t. So how much is the error function? Error function is t minus t plus this. That means if you are finding what is ESST. So this is in the one line I have done the whole process number 3. So ESST is equal to ET, t tends to infinity. So in the first method we have done ES, S tends to 0, SES. The same thing is ET, t tends to infinity, input minus output at t tends to infinity. Input is TUT and output is this. So this I have subtracted. So that means this t and t gets cancelled. What you'll be finding is the whole thing is there. So this thing I have taken here and I have substituted t tends to infinity. So very important part, that is this is a first order type 1 system with ramp input. Okay, in that case what we'll be finding is the t and t of the output and t of the input, they get cancelled. In that case you'll be finding that this diminishing part will be there and this constant part will be there. If you are substituting t tends to infinity, diminishing part will become 0 and only the constant part will remain. So I'll tell you, this is the fifth response and this is the most important response, that is type 1 system with ramp input. And you'll be finding that you are going to find a constant error, that is the constant error of 5 by 4. Okay, 5 by 4 is nothing but 1.25. So input and output will always make an amplitude difference of 5 by 4, that is 1.25, even at t is tends to infinity. So input is also diverging, output is also diverging, but the divergence between these two things are actually constant. Okay, this is a very important thing. Previous case you found out, previous case I had shown you. So this is the response, this is the response of ramp input for type 0 system. Now see, there is a difference. So this is the ramp input of type 0 system. This is input increasing and this is output increasing, and distance between them is actually increasing with respect to time. Okay, so this is the ramp input for type 0 system. Input and output both are diverging, but their distance is actually increasing with respect to time. If you are finding the same thing with respect to type 1 system, okay, in that case input and output both are diverging, but their distance is not getting increased with respect to time, because we have proved it, their distance is actually kept constant at 5 by 4, that is 1.25. So this is the very big difference between the type 0 system ramp response and type 1 system ramp response. Both cases we are going to get ramp output. The difference is for type 0 system, ramp output and ramp input, they are diverging, and type 1 system, they are not converging, they cannot converge, but their distance is constant. So they are like looking like a rail line. Okay, so how much is the steady state error? So at any time, initially it is not there. So initially there is a lag in the output. This is called as backlash or initial problem, that output takes certain time to charge up. Okay, so in that case, that's why this backlash is happening, and because of this backlash there is a distance, time distance between the rise of the input and the output. Okay, and you'll be finding that this distance will be 1.25 constant. So very important thing, and you can calculate the same thing by calculating kV. So kV is equal to limit s tends to 0, s into GSHS. You'll be finding that is equal to 4 by 5. So proof by method 2, and ES is equal to 1 by kV. So 1 by 4 by 5, that becomes 5 by 4. So ESST, that means ET at t tends to 0 by method 2, that is the second method by static error constants, you are finding it is 1.25. And by the third method, what is the third method? Third method is first find what is CT. To calculate CT, you need CS by RS. So this is the CS by RS part, and the CS is equal to RS into CS by RS, and then find what is CS, and then take inverse Laplace, you are finding CT. Subtract this CT from input. So input is T, T minus CT, you are finding this is the part, And this part, there are two things. One is a constant part, one is a time varying part. And there, if you are substituting t tends to infinity, you'll be finding that this static error, so steady state error 5 by 4 will remain. So in that case, this is 1.25, and this 1.25 will remain forever. Very important part. So just do this response very properly. And one very important caution for you, that is how to choose this. How to choose this. That is a divided by s into s plus b. If you are doing it, it will become a denominator. So denominator will be a square plus bs plus a. Choose b and a in such a way that you are finding that this denominator will be so you can do trial and error, but both they should be plus s plus something and s plus something. That is, both should be stable pole. If you are taking unstable pole from the beginning only, you will be finding that output is diverging because output is too much of increment. Okay, so these are the cautions. These are how to design a system. Now we will be going for that is both the input and output go to infinity, it tends to infinity, but the difference between them in magnitude is actually constant. So difference between the input and output, okay, so the difference between the input and output uh, is going to be constant for this system. Okay, this we have to understand. So here both the input and output goes to infinity, amplitude at t tends to infinity, but the difference between them is maintained at a constant value, that is 1.25 here till t tends to infinity. So very significant response we are finding here, and very important conclusion. So this was the type 1 system for ramp input. Now what we are going to find is system for parabolic input. So this is also another important characteristic. So the same thing, GSH is equal to 4 divided by s into s plus 5 that we are taking, and CS is equal to 1 by s cube. So this is RS now. Okay, so CS is equal to transfer function. This is closed loop transfer function. This you have to understand. So this is GSHS is given, HS equal to 1. So whenever I am finding 1 by or GS by 1 plus GSHS, then I am going to get this 4 by s plus 1 s plus 4. So do not get confused. Suddenly ये कहाँ से आ गया? Okay, so this is nothing but CS is equal to RS into GS by 1 plus GSHS. So this GS by 1 plus GSHS is nothing but TS. Whenever you are having trouble, you just go back and start the first numerical. That is this part. Okay, so how this TS is found? How this TS is found? That is TS is equal to 4 by s square plus 5s plus 4. So TS is nothing but 4 by s plus 1 into s plus 4. So whenever you are having trouble, go back to the type 1 with unit step input, and you will find from where you have got this 4 by s plus 1 into s plus 4. So I'm just changing the inputs. So inputs, first case for unit step it was 1 by s, for ramp it was 1 by s square, and for parabolic it is 1 by s cube. Now if you're finding what is CT, CT is a very big component. Here these two parts, because this is 5t by 4 and this is t square by 2, they are actually time varying and increasing part. They will go to infinity as t tends to infinity. The intermediate part, they will diminish and they will become 0 as t tends to infinity, and this CT part, this is a constant part. So if you're finding this response, I have done this by MATLAB also, and I'll be giving you the code, you can check it. This is the input t square by 2, and a t square by 2 is the input, and a is equal to 1 for unit parabolic. And this is also parabolic. Whatever CT I have plotted here, whatever CT is plotted here, from there you can find this is the CT, and these two are increasing, ever increasing. So initially they were less, and as time is going by, the distance between these two parabolic are actually increasing with respect to time. That means their distance or their difference is going to be infinite as t tends to infinite. So it is the same thing is explained here. CT will go to infinity as t tends to infinity. Both the input and output goes to infinity, but the difference also keep on increasing. So ET is equal to input minus output, half t square. This is the input minus CT. This will tend to infinity as t tends to infinity. So this is type 1 system with parabolic input, which will produce a steady state error, and proof by method 2. So by method 2 we are directly find Ka we are finding as 0, and ESST is equal to 1 by K, that is equal to infinity. So error between input and output would tend to infinity as t tends to infinity. So for type 1 system with parabolic input, the steady state error is going to be infinity. Now come for the big part that we could not do last day, that I have taken a type 2 system, that is 2 by s square into s plus 3. So this is GSHS, this is 2 by s square into s plus 3, and here what we are finding is KP. So for type 2 system, there are three inputs again. that is the unit step input, unit ramp input, and unit parabolic input. So what we are going to find is, for type 2 system, unit step is going to produce ESST 0. For type 2 system, unit ramp is going to produce ESST 0. And for type 2 system, unit parabolic is going to give us a finite error. So all these three graphs we have to generate. So GSS is equal to 2 by s square into s plus 3. So Kp is equal to 2 by 0. So Kp we are finding, that is GSHS into limit s tends to 0. So 2 by s square into s plus 3. So this s square are there. If you're substituting 0, it becomes infinity. So ESST is equal to 1 by 1 plus Kp, that is equal to 0. So ESST or steady state error is 0. What does it mean? It means that the closed loop system response is going to touch the input at t is equal to infinity. So CT would touch the input in finite time, or for unit step, for any kind of input. So what will be the response like? Response will be like this. So this responses I will show you, and whenever I give you the same GSHS, and whenever I give you the code, when you do it, you'll be finding this kind of response. So this is actually the unit step response for a type 2 system. Okay, so it will be going up, down, up, down, up, down, and after that it will stabilize. So this is the response, whatever is up, down, unit step response of type 2 system. Okay, and you are finding that after this, all this up, down, the response is going to stabilize at amplitude 1. That means the steady state error between input and output. So this is the step input and this is the output, they are going to be 0. So this exactly this response I can show you. I have already done it. Second case, a type 2 system with unit ramp. So I have not done all this method 3, because you can get everything by using the code that I have generated. So I have calculated it from method 2 only, and I could not show you this outputs during the lab. That's what I have drawn it. And just find out what is KV. So given as GSH is equal to 2 by s square into s plus 3. Why this is a type 2 system? Because there are 2 poles for the open loop system, and these 2 poles are at origin. It is s square into s plus 3. If somebody says only 2 by s square, yes, that is also a type 2 system. But don't take that. You will not be getting the output, because you will be getting sinusoidal oscillations in that case. So take some stable pole and 2 poles open transfer function. You can take s plus 5, doesn't matter, but you will be finding that KV will be equal to infinity, and ESST is nothing but 1 by infinity is equal to 0. So how will it look like? It will look like this. So this is the ramp input. In that case, ESST is equal to 0. That means steady state error is equal to 0, because this is type 2 system and you are giving ramp input. In that case, this will be the oscillation. So around this. Okay, so up, down, and after that, the closed produced by the OT ramp is equal to ESST is equal to 0. So all this response I can show you, and already it is plotted, so it will be shown you. Last response, which is very important, last response which we will show is to plus 3. Input as 1 by s cube. So if you're doing that, in that case, what is going to be? So if you are giving the parabolic Ka, so K is 0 s square into GSHS. So only this kind of numerical will be asked in the exam. The easy, okay, direct constants will be how much is the Kp, Kv, Ka, and accordingly you can find out what is steady state error for step, ramp, and parabolic input. So you are finding that we are finding the error is 2 by 3. So in this case, what we will find is input and output both will be parabolic. Okay, so this is the input inside. This is the input. Okay, parabolic, and this is the output actually. This is the output, and distance between them will be always 1.5. ये 1.5 कहाँ से आया? Suddenly we have found that K is equal to 2 by 3. So this is not the third method I am doing. Here I am not finding the CT and all, because it is getting too big. Okay, so all those calculations I am not doing, but I am showing you what is the second type system error for step, ramp, and parabolic input, because that I could not show you during the lab. So here GSH is equal to 2 by s square s plus 3, type 2 system. You are finding Ka is 2 by 3, and you are finding steady state error. So steady state error is equal to 1 by Ka, that is 1 by 2 by 3, that is 3 by 2, 1.5. That means the same thing that had happened for type 1 system with ramp input, same kind of response you are going to get for type 2 system with parabolic input. So here you are finding that the input will be rising like this. So this is the square wave, that is t square by 2, and here is the output response. And both are going to infinity as t tends to infinity, but distance between them is constant. Initially ये थोड़ा बड़ा रहेगा. Initially there is a backlash time. This will look little big, but afterwards these two distances will be same. So this constant distance of 1.5 at any time will be maintained. So now you have to prove. So I am defining now your work for experiment number 6. You have to show me this 9 outputs and graphs for all these 9 outputs. So code and all these things will be uploaded today shortly. So type 0 system, step input kp, and what is the error? A by 1 plus kp. Okay, so for unit step input, this a is equal to 1. So kp is this, ess is this, 1 by 1 plus kp. Type 0 system ramp input, we are finding that kv is equal to 0, steady state error is infinity. Type 0 system parabolic input, k is equal to 0 and steady state error is infinity. All these three things we have shown. So we have done one type system and we have found out its response for all the three inputs, that is step, ramp and parabolic. So this is very important because here this is going to be some finite value. Okay, so steady state error is going to have some finite value. Second, type 1 system, if input is a ramp step, in that case we'll be finding that steady state error is 0. Okay, and this graph, this table is very important. Any 2 or 3 cases can be asked in the exam. So we'll just mention what is the type of the system and what is the type of the input. You have to tell us what is the steady state error and what is the static error constant. So for type 1 system, if you are giving step input, you are finding that Kp will be infinity and steady state error is 0. We have already shown you that graph, that is input step and output is increasing like this and touching the step. Around 6 seconds, we find that the output is going to touch the input. It depends on different systems. This is the most important response. That is, it is type 1 system and this is the ramp input. We are finding that both the input and output both are increasing parallelly like trend line. Okay, so both are diverging, both are going to t tends to infinity, amplitude is going to infinity, but their distance is going to remain constant, and that distance is going to be given by 1 by kv. Okay, for our case it was something like 7 by 5 or some distance was there. And again for the type 1 system, if you are finding parabolic input, then the distance between the two parabolas are going to be divergent. So one parabola and other parabola, they will be divergent in nature. Next is type 2 system. For both unit step input and unit ramp input, you will be finding that steady state error is 0. But very interesting kind of graph you are going to get. This is the unit step input to a type 2 system, and this output is oscillating. So output of what? So given is open loop transfer function, but we are finding output for the closed loop negative feedback system, CT for the closed loop negative feedback system. So by this whole study, we are actually predicting the stability of the closed loop negative feedback system from open loop GSHS. So this is a very important thing. I told you at the starting of the session that from the open loop transfer function, we are trying to predict what is going to be the output and what is going to be the related stability. So this is the type 2 system with step input. You are finding steady state error is 0 because output is following the input. This is the type 2 system for ramp input, and you are finding the same thing, that is the output and input, they are actually touching each other and then going forward. And lastly, type 2 system with parabolic input. And as we have found out, the type 1 system with ramp input, that both are going to infinity, but distance between input and output is constant. Here also, these two parabolas, you will be finding they are behaving like a trend line. Okay, and their distance between them is going to remain constant. So that is this part. So these diagonal elements are very important. So practice this first. That is step input to the type 0 system, ramp input to the type 1 system, and parabolic input to the type 2 system. Okay, they are going to produce some constant kind of error, or ESST is going to be present, and this is going to be a finite value. And other things, they are going to be 0 or infinity accordingly. So these are the graphs that I wanted to show you. And